At 0747 a.m. Eastern Time, October 29, 2025, three independent observatories, SOHO, Stereo A, and the GOES 19 coronagraph, registered an anomaly in the light signature of the interstellar object 3I Atlas. At that exact moment, the object was at perihelion, 1.36 astronomical units from the Sun, within the region of maximum solar flux. The instruments had been calibrated for thermal variance, spectral drift, and cosmic ray interference. None of those corrections changed the result. Across all platforms, the reflected spectrum of Atlas appeared distinctly bluer than our star. It began as a background cross-check. Solar physicists at the Goddard Space Flight Center were processing coronagraph data to isolate plasma filaments when a junior analyst noted that the apparent color temperature of the object exceeded that of the photosphere, a result physically inconsistent with any known cometary body. In visible wavelengths, Atlas should scatter sunlight reddened by dust, typically peaking near 5,000 to 5,400 Kelvin. The readings instead corresponded to an effective blackbody temperature approaching 6,200 Kelvin. Even after compensating for instrumental bias, the object remained anomalously blue. The finding was verified within hours. The Solar and Heliospheric Observatory's LASCO C3 camera confirmed an identical spectral deviation using independent calibration sequences. The Japanese Hinode mission provided corroboration through narrow-band ultraviolet imaging, recording a reflectance ratio indicating the emission of photons at shorter wavelengths than sunlight itself. In practical terms, Atlas appeared to radiate light that was not merely reflected, but enhanced. For context, no known comet or asteroid has ever exhibited a color index bluer than the solar standard. Dust grains, organic tholins, and water ice all scatter preferentially toward the red as they heat. Even active comets undergoing violent sublimation remain cooler, dimmer, and redder than the Sun. The laws of radiative transfer do not allow a cold body to outblue a stellar surface at 5,800 Kelvin. Yet the data remained consistent across instruments separated by millions of kilometers. The calibration logs were re-examined. No sensor drift, no software error, no solar flare contamination. What remained was the light itself, coherent, verified, and unexplained. By late afternoon, Harvard astrophysicist Avi Loeb had classified the phenomenon as the ninth official anomaly in the Atlas file. His report phrased it cautiously. Apparent spectral shift suggests emission from an energy source exceeding solar temperature. The language was careful, the evidence precise. But within every lab that reviewed the data, one fact was undeniable. If these measurements are correct, then an object now passing through our solar system is radiating with a color temperature higher than the Sun, and no one yet knows how. The first irregularity lay not in what was seen, but in what persisted after every correction was applied. When the raw spectral data from 3I Atlas were cross-compared with solar baselines, the bluing effect did not dissipate under normalization. The slope of the reflected spectrum, measured between 400 and 600 nanometers, remained inverted, a sign of higher photon energy rather than lower. The result was identical in both coronagraph and ultraviolet channels, implying that the anomaly was intrinsic to the object, not a product of instrumentation or angular scattering. In known cometary physics, this behavior is prohibited by temperature constraints. The surface of a comet at 1.36 astronomical units should not exceed roughly 300 Kelvin. Even freshly exposed metal ices heated by solar flux radiate primarily in the infrared. To produce light bluer than a 5,800 Kelvin photosphere would require either an optical illusion, a chemical emission line misinterpreted as continuum shift, or a process entirely outside the thermodynamic envelope of natural materials. Each possibility was tested, and each raised new contradictions. The first explanation proposed was compositional. Some researchers suggested that Atlas's surface might contain unusually reflective silicates or metallic grains acting as partial mirrors, selectively scattering shorter wavelengths. However, the albedo required to reproduce the observed spectrum exceeded any measured natural surface, approaching values typical of polished alloys. The theory could not reconcile the concurrent ultraviolet excess, which implied active emission rather than reflection. A second camp proposed that fluorescence could account for the readings. Volatile compounds, perhaps cyanide or nickel carbonyl, might absorb ultraviolet radiation and re-emit at shorter wavelengths. The mechanism would mimic the appearance of a hotter body without violating thermal laws. Yet laboratory spectra of those molecules produce narrow emission peaks, not the broad continuum slope now observed. The shape of the Atlas spectrum was continuous, smooth, and stellar in character, not molecular. The most cautious interpretation remains instrumental cross-contamination, sunlight scattered through the object's coma into the coronagraph optics, artificially elevating the apparent color temperature. But repeated calibration tests have failed to reproduce the pattern under controlled simulations. The data, for now, resist all correction. Each hypothesis explains fragments and leaves the whole untouched. The object behaves as though radiating energy beyond its thermal capacity, yet every verification procedure confirms the readings. In the absence of direct observation, Atlas still half hidden behind the sun, the scientific community is left with a paradox, both measurable and inexplicable. Only continuous monitoring, as it reemerges into view, will reveal whether the bluing was an illusion of geometry or the first recorded signature of an unknown energetic process. For mission control, the chronology of Atlas is now divided into windows of opportunity, each measured not in days but in degrees of solar elongation. Every hour that passes shifts the geometry between Earth, the Sun, and the object, tightening the corridor of observation. When the perihelion sequence began, the object was already descending into the zone of optical blackout, less than 30 degrees from the Sun. Telescopes across the globe were forced to suspend direct imaging, their instruments locked by automated safety protocols. What followed was a transfer of responsibility. From ground observatories to spaceborne coronagraphs, from visible light to radio and plasma telemetry. At first, the transition seemed routine. The Stereo A spacecraft continued to record the broad light curve. The LASCO coronagraph at L1 maintained partial coverage, and deep space networks prepared to track any deviation in trajectory once Atlas emerged on the opposite side. But as the brightness readings continued to climb, the timeline lost predictability. Each model projecting the object's visual magnitude, a crucial indicator of dust and gas release, diverged from the next. The standard sublimation curve for comets near 1 astronomical unit could no longer fit the data. What should have dimmed with increasing phase angle instead intensified, as if some hidden mechanism was countering the glare of the sun. Now the countdown is measured not by clocks, but by orbital mechanics. Within 2 weeks, Atlas will begin to reappear from behind the solar limb, faintly visible to the Parker Solar Probe and the GOES 19 platform. In that interval, no terrestrial telescope can intervene. The object travels through a region of space saturated by radiation and magnetic turbulence, a zone where information arrives only as numerical telemetry, delayed by millions of kilometers of distance. Scientists describe it as an era of waiting, not silence, but signal sparsity, where every fragment of data could redefine a decade of models. Beyond this period lies the reemergence window, the moment when reflected light will first separate from the background corona. If Atlas retains its anomalous blue shift, the result will be instantaneous and unmistakable, a point of light brighter and colder than it should be. Until then, the solar system itself functions as a barrier, hiding an object that continues to defy energy balance and thermodynamic law. Each orbiting instrument is now aligned, counting the hours to reacquisition. What surfaces in that data will determine whether Atlas remains an astronomical curiosity or becomes the first confirmed deviation from natural behavior in interstellar space. In the days following perihelion, official communication narrowed to a trickle. NASA's Solar Dynamics Laboratory released only baseline telemetry summaries, no imagery, no spectra, no commentary. The European Space Agency published identical figures with marginal differences, suggesting a coordinated embargo rather than a lack of data. Requests from research institutions were acknowledged but left unresolved. Within professional channels, discussion shifted from open exchange to encrypted correspondence, where even senior investigators spoke cautiously of instrument calibration pending and data still under internal review. This restraint was procedural on paper, but palpable in tone. Teams that had shared preliminary spectra in real time now waited for authorization to publish. Conferences scheduled to analyze the perihelion phase quietly postponed sessions without explanation. The absence of official interpretation became the story itself, a silence dense enough to imply significance. Independent astronomers began to compare the released coronagraph sequences frame by frame. The expected reappearance of Atlas, the first measurable signal beyond solar conjunction, did not occur where orbital prediction placed it. The discrepancy was small, less than a tenth of a degree, yet far beyond the margin of error for an object tracked by three simultaneous instruments. At the same time, one dataset slipped through. A short telemetry batch from the Stereo A probe, recorded during the blackout window, showed an unexpected rise in short wavelength photon counts. The reading was transient, lasting under 90 seconds, and accompanied by a faint spike in local particle flux. Its origin point aligned precisely with Atlas's calculated position behind the solar limb. No solar flare, no coronal mass ejection, no instrument anomaly was reported. The file circulated internally under the designation Event 29-7. That was the moment the narrative shifted. A single observation, verifiable yet contextless, introduced a new variable: emission. The object had not merely reflected light, it had produced it. After that confirmation, the tone of communication changed again. Press officers referred inquiries to ongoing analysis. Data archives were locked, pending verification of energetic source. And for the first time since discovery, all agencies monitoring 3I Atlas synchronized their schedules for a coordinated announcement. When the embargo lifted 48 hours later, the update contained just one confirmed statement. During perihelion, the interstellar object designated 3I Atlas emitted independent radiation consistent with temperatures exceeding the solar photosphere. The transmission ended there. In the aftermath, what remains are numbers, stable, verified, and deeply uncooperative. The spectrum recorded during perihelion shows a sustained emission peak beyond the blue threshold of the sun's photosphere, cross-referenced by three instruments corrected for angle, dust scattering, and cosmic interference. The result holds. Atlas, a 5-kilometer interstellar object, radiated light implying temperatures no natural surface could sustain. The data are now archived in open repositories, reviewed by peer committees, and translated into models that all return the same conclusion. The object behaved as if self-luminous. What this means is still uncertain. Most teams treat it as an unknown energetic phenomenon, not yet classifiable. The working definitions vary. Some describe a surface reaction triggered by extreme solar bombardment, a transient plasma envelope, perhaps unique to interstellar composition. Others propose a resonant interaction between metallic compounds and solar magnetic fields, capable of producing coherent re-emission. These remain hypotheses built on incomplete parameters. None yet explain the persistence of the spectral shift or the absence of expected decay once the object receded from perihelion. The data are factual. Their interpretation is still provisional. In professional terms, the Atlas event has become a new reference point, not proof of technology, not proof of natural law, but proof of limitation. It marks the boundary where observation reaches its current precision and still fails to supply causation. For astronomers, that is both a constraint and an invitation. Instruments now being recalibrated for the post-Atlas survey will carry enhanced ultraviolet sensitivity and higher temporal resolution, designed to detect any recurrence of such emissions. The protocols that govern this observation, will form the template for future interstellar monitoring campaigns. The methods will evolve. The uncertainty remains. What is certain is that the object continues outward on its hyperbolic path beyond the plane of the solar system. It leaves behind only light curves, data archives, and the awareness that something passed through our neighborhood, behaving in a way we were not prepared to describe. The event has already entered textbooks as an unresolved case study, a line where physics and probability diverged. Beyond that line lies only continued observation. Whatever Atlas was, artifact, anomaly, or accident of nature, it has altered the vocabulary of what we call possible. The next interstellar object will arrive eventually, and when it does, every telescope will turn toward it with a single unspoken question still hanging in the space between data and belief. Will it shine the same impossible blue?